So, good morning, everybody. This is going to be a tough act for me to follow. Steve already gave away a lot of the good, juicy stuff, but I'm going to talk to you, as he said, about some of the nuts and bolts and some of the challenges that we really faced as part of this project. It was a very exciting project, as you might imagine. A lot of twists and turns, a lot of challenges, a lot of late nights, but happy to recount that story and talk to you all about it here this morning. So. Today I'm going to talk about how this project team responded quickly to this critical find, some of the challenges that we faced, and really we'll focus in on the three-phase approach to repairs that made it possible for this bridge to reopen in just 83 days after the fracture was discovered. Let's talk about some of the critical things that were established in those first 24 hours that helped make this project a success. We really brought together a core veteran leadership team that had been involved with a number of different emergency projects. So that gave us a really good understanding of what needed to happen in these early days to make the project successful, make the recovery successful. Several of our core leadership team had already cut their teeth on a number of different emergency projects, including the Brent Spence Bridge fire last year and the Sherman-Mitten Bridge, which was, if you don't know about that bridge, it's almost a sister bridge to the Hernando DeSoto, same shape, same designer, and really a lot of the similar details there. So that gave us a lot of really legwork going into this that helped us to navigate through there. So we brought a number of those lessons learned to help solve this problem and really move things forward. Some of those key steps that we had early on in the process were really to immediately get our hands on as much data as possible. We started gathering bridge plans, shop drawings, inspection reports. Both TDOT and RDOT were very helpful in getting us the information that we needed, and that was really crucial early on to start diving in and understanding the details, what exactly we were dealing with on this bridge. Simultaneously, we started out by organizing our teams internally. Steve mentioned 60 engineers on our team. Trying to get that many people going, you don't obviously onboard them all at the same time, but we started by breaking it up into different teams and different functions that we knew were going to be needed initially off. So we got those teams engaged on day one, and we really started brainstorming, as you'll see, to some of the solutions just that evening, with as much information as we had. So Steve also mentioned the criticality of communication. I've got up here on the screen behind me here the daily meeting schedule, and you can see there's quite a few of those stacked on top of each other, and that's for a reason. I mean, things are changing on a project like this hour by hour, minute by minute. So really communication is key. There's a lot of interested stakeholders at a lot of different levels. Everybody needs a little bit of different information because they've all got people that they have to answer to and people that they have to update, as well as media, politicians, the whole 9 yards. So keeping people informed is a full-time job on something like this, and you got to plan for that. You can't just pull your lead designers into these meetings and expect them to be productive outside of the meetings as well. It is a bit of a disruption. So having redundant people involved with tasks and being able to speak to what's going on is really kind of a key thing there. One of the things that we found to be very helpful in some of our other projects as well, and we brought forward to this one, was the preparation of daily work summaries. Just at the end of the day, we prepared a work summary, delivered that to RDOT and TDOT so that they knew what we had accomplished that day and what our next day tasks were, so that we always had a line of sight moving forward. Very important to kind of keep everybody focused on where you're at and what's going on. I'll throw the project timeline up here. This is a very simplified timeline that actually Kiewit prepared, but this is the full 83 days of the project. And as you can see, we began work on multiple phases on day one. Really that first week was full of a lot of activity, as you might imagine, trying to get our heads around the problem, answering questions from the Coast Guard. Steve was dealing with traffic issues. Inspections ongoing, and we're trying to kick off the repair plans, both in multiple fronts there. So again, 60 people on a project, this is how it kind of gets done, is over a schedule like this. During those early days, immediately following the fracture, our team was still out there, and RDOT, as Steve mentioned, got onto the site, and there was a real effort there to monitor that fracture throughout the day. We wanted to make sure that things weren't changing. The bridge is undergoing different cycles. It's moving thermally. We wanted to make sure there was no crack growth or nothing going on there. So both RDOT and Michael Baker used drones to monitor and scan the rest of the bridge, make sure there weren't any other fractures that could be found. We also used those drones and photography to monitor the crack to make sure there wasn't any growth going on. The other thing that was really critical as part of our operations, we needed to understand exactly what the state was of the fracture, as you can see from the many photos that were taken up here. And this is where Jeff comes in. Jeff's one of our lead rope access inspectors, and Jeff volunteered for this very critical mission. He was going to go out there and get us as much data on this fracture as possible. So we organized a live video feed using our drone. We were able to take that live video feed, push that out to YouTube through a secured channel, and we set it up by a WebEx. And what this did was it really allowed all of our engineers that were spread in different offices to be able to communicate with Jeff as he's out there taking measurements, taking photographs of key interest areas. And one of the things that we had to document, or we really had to get a handle on, was how much twist there was in that tie girder and how far back it went. That would be critical to know so that it affected our phase one repair details, as you'll see earlier on. So we really felt like this was a huge, huge accomplishment. We were able to get a lot of information within minutes instead of within hours just by being able to do that. We didn't have to remobilize anybody out there. We were able to collect all the data that was needed in one fell swoop. And it gave us a lot of confidence moving on with that critical information for our analysis and our repair teams to use. You know, one of the early questions, obviously, everybody wanted to know was, how bad is this? How bad is bad? We really had to get our handle on the severity of the situation. Is the bridge safe? Is it safe to work on the bridge? Those were the key fundamental questions that we had to answer. So we started by looking at the stress levels in the tie. We just did the simple P/A, confirmed what was on the original design plans. We're looking at somewhere around 38 KSI, well below the 0.55 FY allowable. So we did a quick calc. We removed the fractured sections of the box, and that's pretty representative of what was removed out there by the fracture, the entire top plate, the web plate, and 10 inches of the bottom flange. That leaves you with about 45% of the overall section. Well, doing the math on that, that takes your P/A up to 83 KSI, well above that 0.55 FY limit. So, okay, we know we're a little bit outside of the comfort zone there, but we haven't yet accounted for any kind of eccentric loading, right? We've got an angle now that's, you know, eccentric to this box. What's going on there? You could see from some of the previous photos there was some distortion going on. We needed to understand just how much that eccentricity was really driving things. So we went in and conducted a refined analysis. And that refined analysis was very telling. It actually showed us very similar behavior to what was seen out there in the field inspection. You can see here some of these areas where there's a little bit of clear elements right in here. These are actually yielded elements in the model. We were actually just able to see that same yielding pattern on the lower flange out there in the field. So we've got some localized yielding, we've got some eccentricities, but you know, really how much? The model showed that we had, you know, very limited reserve capacity on that member, and essentially where we were at was, you know, there were a lot of unknowns still at this level. You know, this is a day, 2 days into the analysis process, into the project. We didn't know the actual force in the tie, right? You have estimates, you have plans, but things are different in the field. There's always redistribution of load, but how much redistribution of load? Transient loads, wind loads, thermal loads, other forces affecting the structure, the strength of the materials, the condition of the welds, all a lot of questions that we didn't really have answers for. Yet we knew that we were working in very thin margins, and we had to be extremely careful with the work that was being done out there and being proposed. So the modeling, as you can see, was very important. We took a very measured approach going through and getting our models together because we knew they had to be right. We started with some very simple 2D models, built those out, and compared those to the existing plans. We got good correlation from there, so we take the next step forward. We looked at a 3D model so that we could capture the full aspect of the structure. We knew that the behavior was potentially going to go to alternate load paths, so we had to make sure that the stiffness of the structure, the boundary conditions, everything was modeled as accurately as possible so that we could predict the structure's behavior as best we could. So that was all critical modeling assumptions. You know, one of the other things that we did early on was we understood the importance of information. Being able to communicate that information out to stakeholders, public involvement specialists, our own internal teams, being able to mock things up. So we started the development of a BIM model on day one. We knew that was an investment that would prove very useful for those visualizations. We also knew it was going to come in handy for any kind of clash detection. And we used this model throughout. You know, Steve showed it in some of his photographs as well. That was really instrumental for us in terms of proof of concept. Will these things fit together? Will we be able to get in there? And it was useful to discuss and have dialogue with Kiewit on as well. Another key aspect that I really want to focus in on is the quality assurance. We started this modeling task on day one. We knew we didn't have time to back up if something was wrong. We knew we had to get concurrence every step along the way. So we devoted 2 teams to independent modeling. We had one using a Midas software, which is our in-house tool that we use all the time, and then we had another group out of our Chicago office running Larsa. And those 2 teams advanced their models simultaneously. They were lockstep all the way, checks and balances. They would work through any boundary condition issues and come to an agreement so that we made sure that we had good, solid foundation of modeling there so we could trust our results, because that was critical. And then on top of that, we had another level of senior QA to make sure that those 2 folks, that the modelers weren't just kind of fooling each other as well. So very important to make sure that you have that kind of quality control, and taking the time to get that set up and make sure that you're moving together really helped to expedite this overall project and deliver it a little bit more quickly. So again, knowing that stress state in the tie was really critical to our understanding. We didn't want to do anything to overstress the tie, and it really influenced our repair options. We had to go a little bit beyond our normal modeling approach, using an elastic analysis because of the yielding that was seen in the deformations. So we did utilize both material and geometric nonlinear models, taking incremental time steps to make sure that when we're doing anything as far as loading or unloading the tie, we're getting the true behavior of those materials that are going to be yielding and going to be ineffective in that. So very important part of the modeling process. So here you can see our detailed finite element models. We used those both in isolation, and we dropped them in our global model. That gave us a real feel for the behavior of the deformations in the field. And as you can see, there's pretty close correlation. That deformed shape was very similar when we saw it and we actually pulled that thing apart. So it was very important for us, for our future discussions about repairs and unloading the tie. So all this is going on this first week, right? And I haven't even talked about the repairs yet. We've got a lot of things going on. The find occurred on a Tuesday. By Friday, we had draft plans, and we'd sourced the material for stabilizing the splice. And as Steve mentioned, TDOT made the decision to advertise for a contractor for part of a CMGC process. On Monday, Kiewit was onboarded, and they immediately hit the ground running. So, let's talk a little bit more about this phase 1 stabilization here. And I want to talk more about this temporary fix. There's not a lot of relevant examples out there for how do you stabilize something for 4.5 million pounds. That's a lot of load. To get your head around. We looked at other bridges and other projects that had fractures, and they weren't dealing with anything of this magnitude, right? A tied arch has a tremendous amount of load going through that tie girder. This was all 100 KSI steel and a very significant loading. So we had a brainstorming session just initially. What are all the ideas? Has anybody got any good ones? How do you fix it? Do we go straight into the permanent fix? Is that an effective thing? Well, no, probably not. The duration's just going to be really long. We were very concerned, as you might imagine, about the stability of the bridge, so we had to make sure that was covered. We talked about shoring towers, but that had impacts to navigation, obviously a long lead time associated with that. Temporary post-tensioning, well, that's a great idea. You can kind of see that over here in this little second screen over here. But the detailing, the fabrication, getting that to work for 4.5 million pounds is no small feat. That kind of led us to the more permanent fix discussions. We talked a lot about an adjacent splice, and that's where we started here. Just coming out here and putting some bolts in there and putting a stabilizing splice over top of that fracture. Okay, well, we had a little bit of concerns about the distortion of the box, as we talked about. So we started gravitating towards, lengthening that splice out a little bit. And that was our initial design that was submitted on that Friday to the contractors, was lengthening this splice out, getting away from the fracture, utilizing the existing splice here on the left-hand side to tie back into. So we started working through that. We got the availability of the materials. We worked through that. Stupp Bridge out of Bowling Green was very helpful with that. They kind of raised their hand, said, we've got some material you guys can use. It's a 2¼ inch plate, HPS 70. Got these links available, so we'd be happy to help out. So we started working with them a little bit on the material side, making sure that we had everything lined up for when Kiewit got on board, and we could execute that, bring that to construction. So, as I mentioned, as it was mentioned earlier by Steve, they brought that constructability input to the team. Very crucial for a project like this. They also brought a hefty appreciation for the risks involved in doing this type of construction, right? Obviously, we have a very severely damaged member out there, compromised. So that risk was weighing heavily on everybody's minds. From day one of the project, we talked a little bit about that, and we were concerned with working immediately adjacent to that. They brought that same concern, and matter of fact, they were very concerned with the idea of rattling out these bolts immediately adjacent to that fracture. You know, again, you've got a very highly disturbed region. Everything's right up around 100 KSI yield. Don't really want to mess with it. So we kind of collectively worked together to come up with a solution to lengthen the overall splice plates. We got the longest plate that STUP had available, slapped that out on the outside, and put those splices as far away as possible so we weren't doing anything to disturb that. On the inside, because of limitations between the floor beams, we had to go with a little bit thinner plate or a little shorter plate. But you know, ultimately got those splices as far away as we could as possible. So this was really the new direction that the team took collectively, and we put that into action. So again, Kiewit was onboarded on Monday. By close of business Tuesday, we had a full new design ready to go, released for construction plans, ready to go out the door, and fabrication began the next day pretty much on that. So they developed the shop drawings and everything else. And from the BIM model here, you can kind of see what that looks like, what the overall phase one repairs are. Again, there's a plate here on the inside, which is a little bit hard to see, that kind of goes from this T bracket all the way to that T bracket there. But you can get a sense for, you know, overall how much that was lengthened. We started with a connection that was over here and ran to about there. So really, you know, that was one of the innovations, was to kind of come in here and reduce the risk for the project and help control that. So fabrication began just 10 days after the discovery. STUP worked around the clock, really cutting plates, pre-drilling the holes. TDOT picked up those plates and delivered them on Saturday to the project site, and Kiewit began to hang that steel. One of the things that Kiewit also brought was another idea of how to do this. When we advertised this, or when TDOT advertised it on that Friday the 14th, they had put it out anticipating that the team was going to work from the river. They'd actually asked for marine qualifications, and Kiewit kind of proposed in there to use this chain fall system, an innovative idea to limit the weight on the bridge. So you can kind of see that there in the background. What they did was they brought the plates out across span B, which was the undamaged span, brought them out to the central pier there, and then from there used a series of come-alongs to kind of swing the plate into position, drop it over to the side. They did have a number of, as Steve showed before, the platforms underneath the bridge so that workers could immediately access, do the bolting and the drilling. And throughout phase one, we were intentional about limiting the loads on the bridge. We didn't want anything more than 80,000 pounds in that damaged span. The 80,000 pounds basically came from the acknowledgement that we knew the fracture had occurred at some point in time, the complete fracture that we were dealing with, some point in time prior to that inspection. We knew a single 80,000 pound truck had gone across that bridge in the worst place possible. So that was our safe working zone, safe working load that we dealt with on that. We wanted to make sure that we were comfortable with that. Again, no work was performed from the water, and the installation was completed within 2 weeks after the initial discovery. So here's a couple of additional photos of the phase one repair. Again, that inboard splice plate was only half height of the web height, added some additional capacity. Those little T stiffeners that you see at the end in the photo behind me there, those were actually added to counter an eccentric couple that was developed. We had to get those plates to clear the existing connections. They had to come about 3 inches off of the existing steel. So that developed quite a large eccentricity. Plus you had the 2 plates dropping at different directions. Gave you a bit of a couple at the end of the bridge that we had to, or at the end of the splice plates that we had to account for in the case that something were to let go. So we worked those in there and added those details as well. So now I'm going to pull you back in time, back again to day one, so we can talk about the simultaneous effort that was phase two to really start developing the long-term solution. And our initial charge there was to preserve the capacity of the tie. This was really a challenge because of the thin sections between the connections at this bridge. Hazelett and Nerdahl designed this bridge, and one of the features that they had done on both this and the Sherman Minton was using 100 KSI material. They wanted to be very efficient with that material. So in the free length between connections, you've got a thin 1 3/8 inch plate. When you get out to the connections, it's actually doubled up to about 2 1/4 inches in thickness. The reason for this is net section. They didn't have enough meat in that thinner plate to put any bolts in it. So as soon as you put bolts in there, you've reduced the capacity. And they relied on these full penetration welds at every one of these connection locations. That led to a lot of potential issues along the length of this bridge. Obviously, we had a fracture at a welded joint. So all those connection plates were upsized to account for that net section, and that meant that we would have to come back in. If we wanted to avoid reducing the capacity of this tie, we were going to have to tie back in at those connections. So we began developing a scheme to unload the tie using post-tensioning. You can see here just a couple of the early calcs that we had from that very first night on the project. And then, multiple concepts were considered. We didn't have the initial solution. We had to fit the geometry, so to speak. We had to figure out how to carry that 4.5 million pounds. So we looked at bars at the sides, we looked at bars on top and bottom, we looked at strand, we looked at bar, we looked at multiple methods of jacking. Ultimately, what drove the decision was the load path. The tie girder consists of two very thick web plates on the side and essentially cover plates on the top and bottoms of the boxes. And so transferring that load had to be done through the side plates, through those existing connections. So the arrangement of getting the PT into those seemed to make a lot of sense. The initial thought was to replace one field segment about 75 feet of the tie. That grew into two segments after the phase one modifications were there. So originally we planned to take that tie fully out, and thankfully we kind of came around and left it largely in place and plated around it. So we did end up taking the fracture. I'm not going to get into the details of the PT system, but that final PT system was detailed to take about 2 times the dead load force. We wanted to be certain that we had something very robust out there to make sure that we handled it. We've already talked a little bit about that BIM model. Here's some photos of the weldment that was out there, as you can see, using the existing bolt holes to connect back in and transfer the force from the rods, PT rods, to the tie. And a unique detail there of a cheese plate and a double nut. We had to actually exchange every bolt out one by one in order to connect this weldment into position there. So that was an interesting part of the project. Just some more construction photos, the struts and the whalers of the anchorage, PT bars there as well. Stressing was performed by DSI using their standard jacks. And Kiewit worked with DSI to develop a jacking plan, comprehensive monitoring plan as well. So we had strain gauges located throughout the bridge. We also had the Dynaforce sensors, so we knew how much load was going into the PT system. And we also knew how much load was being shed other places. This was very important and very critical because we didn't want to overstress any of the other locations on the bridge. As Steve mentioned, all the other welds were being inspected. We didn't know at the time we were performing the work the condition of those welds or anything like that. So we had to make certain that all of that was being done within safe limits. We basically limited to what the design live load was, plus a factor of safety. So we monitored the drag force, which is the force outside of the structure being resisted by the rest of the structure, to make sure that it didn't overstress any additional members there. Stressing operations started on Father's Day. On day 2 of the stressing, the fracture was removed, giving us our real first glimpse of the fracture. You can see that in the far right-hand side, and you probably can't get in and see enough detail in that image to really tell, but it was pretty evident there were some pretty poor welds in there, so that was our culprit. That right photo is the 2 halves side by side, if you can see that. And then the phase 2 plating was designed to be fully redundant over the full 150-foot length of the repair, so we had 2¼ grade 70 plates from WWFco installed in 10 days around the clock, pretty much on that. Squaring up the box was a little bit of a challenge, but the iron workers brought some ingenuity, came up with a system of come-alongs to nice and gently kind of tug that back into place without too much force. So we ended up getting that within about 1/4 inch of square, which was a real accomplishment. And then this is a completed photo of the phase 2 in all its glory. Steve already mentioned the inspection efforts. I won't go into that. We did map all of the locations that were found as part of that inspection and address those in phase 3. So you can see up here the little red circles represent small defects that were cored out of the tie girder, and then the blue lines represent some additional plating that was done. And we used basically the same phase 2 plating with the following exceptions. We didn't use any PT in there, okay? We didn't want to carry that system from joint to joint down the bridge. So that was an acceptance really that we were going to have a small reduction in capacity, but still well above the design live loads for the structure, design loads for the structure and strength limit states. We did also introduce some chamfered ends that you'll see on there, kind of old school detailing to reduce those net section impacts along the length of the bridge. All in all, we cored out, we plated 17 locations, cored out another 8, and had 21 defects ground out of this tie. Those defects, by the way, a lot of those were showing up on the inside of the box where it was completely inaccessible to previous inspections. You had sealed end diaphragms on this bridge, which made it a challenge to find some of those defects, therefore the NDT that was used. We did take into account some constructability input from phase 2 and incorporated that into phase 3. You'll see the 4 little holes in the even joint there, that the existing bolts were left in that splice plate pattern to hold all the plies of steel together. We had to remove every single one of those bolts, fully drift pin that to get those plates on. Those 4 bolts were left in place just to hold that sandwich together to keep everything from shifting. That was something that the contractor noticed during the phase 2 problem, or phase 2 repairs. And then just a few photos of the fabrication. You can see here the odd joint plating. Essentially, it almost looks like a Band-Aid. Wasn't intentional, but that's the way it kind of ended up. We ended up getting 2 welds for the price of 1 with that, as there were 2 welds on each side of the floor beam, 1 on each side of the floor beam, inside and out. And you can see the inside plate detail that had to pass through the floor beam there as well. A couple more photos of the installation process, and then as Steve mentioned, the combined 3 phases were completed within 83 days, and the bridge was returned to service with no reduction in load posting whatsoever. So a real success for the project. You know, just a real quick recap, lessons learned. This was the 4th emergency project that I've been involved with, so it's really amazing to me still to this day how much can be accomplished when everybody's working together to solve a problem. You know, there's no finger pointing, there's no blame, everybody's just united. They may not know what they need to do, but they're definitely willing and able to step up. And then projects like this, as we talked about, require an incredible amount of communication. You just got to accept that, plan for it, and understand that the folks that are involved in those meetings aren't going to be doing production work for you. They're just going to be engaged in that process to a great degree. TDOT's decision to utilize the CMGC process, in my opinion, was a pivotal one. It really helped to expedite the project, and I think CMGC is a wonderful method that can be used on major rehabilitations. It really brings a lot of great attributes together for the success of the project. And just, you know, on a project like this, you got to be prepared for everything. So I'll leave you all with some of the by the numbers. You can read these and just take a look at those. And I want to thank you all for your attention today.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.